Question of the week from the Naked Scientists.
This question comes in from Christy. She says, I was stirring some sugar in some water the other day to feed my bouquet of flowers, and it occurred to me that sugar would dissolve faster in hot water. Why do powders dissolve faster in heated liquids? Another example I can think of is Jell-O powder, which wouldn't dissolve at all if your water isn't hot. There's a little bit to unpack there, Philip. Let's take the first part of the question. Why do solid sugar granules dissolve faster in hot water?
Okay, so the thing that you've got to work out is sugar is a relatively small molecule, and inside a granule of sugar, there are lots of those molecules packed together, and they have bonds or interactions between them that are holding them together. To dissolve it into the solution, what you need to do is separate all of those molecules out from each other, so break those bonds holding the molecules together and replace those with interactions with the solvent molecules. Water is quite a good solvent for sugar. It will dissolve relatively easily. But the more energy you put into the water, so the hotter you make it, the easier it is to break up those bonds that are holding the sugar molecules together. And the faster the molecules are moving, so the more times they'll collide with each other, the more opportunities there are to transfer that energy and make that dissolving happen.
Christy suggests correctly that sugar will eventually dissolve in cold water. It'll be slower, but it will eventually dissolve. Whereas with a different solid, Jell-O or jelly, it will only dissolve into the solution if there is enough energy in the water, if there's enough heat. What's the difference?
Okay, so sugar is quite a small molecule and it's quite soluble in water. Jelly is a much bigger molecule. It's actually a protein, so its chemistry is quite different. The way it interacts with the solvent, the water, is a little bit different, but mostly it's because it's a much bigger molecule, and those big molecules have a lot more bonds between the molecules, so it's much harder for the water to break them apart. It takes much more to get in between the chain, the gelatin protein, to break them apart and dissolve them in the water. In fact, they never really truly dissolve in a sense. They make what's called a gel or a colloid. That's how jelly is happening. When it's warm, it behaves kind of like a liquid. It's sort of like a solution. But as it cools, the chains, the proteins start to stick back to each other and try to make a solid. But in doing so, they trap water in between them. So instead of making a kind of dry, powdery solid, they make a gel or a jelly.
To take Christy's question a step further, we've only talked about one part of the equation here, which is the solid water's remained consistent throughout what we've discussed so far today. What happens if you change the solvent? If you try a different liquid, how does that affect the chemistry?
Different liquids, different solvents, if you like, are good at dissolving different things. It's a kind of like with like sort of situation. Water is what we would call a polar solvent. It has oxygen and hydrogen, and they have a difference in charge. So it has bits that are a bit positively charged and bits that are a bit negatively charged, have more electrons. And that will it would be good at dissolving things that are also a little bit charged or have this similar property. But if you take another really good solvent, petrol, something like that, which is completely different, it has almost none of that polarity, none of that charge, but it's very good at dissolving things that are very similar to petrol. So if you've got some, say, glue, which is often a long polymer, not very polar, and it's sticky, and you want to get rid of it, often it will be more easily dissolved in something that is a bit like petrol, a bit like oil, a bit kind of fatty, or what we would call non-polar, compared to things that dissolve in water. That stuff won't dissolve in water, but it will dissolve in a more non-polar.
There's some interesting chemistry that goes on with regards to this dissolving process, where the reaction can give off heat, or it can take in heat in the liquid, or reduce the heat in the liquid, can't it?
Yeah, and I mean, when we're doing chemistry in the lab, we're always going to try and pick the best solvent for the process that we're doing. And sometimes you might use a mixture of different solvents, or you might use different solvents for different parts of different processes. When you dissolve things, the temperature will change just through the process of dissolving. So we're not making the solution hotter to try and dissolve it. If we put the powder or the solid that we're trying to dissolve into the liquid, and then it will either get colder or hotter. Some examples of this: if you dissolve sodium or potassium hydroxide, caustic soda, into water, it can get really hot, and that can be really dangerous. If you've ever tried to use those chemicals for cleaning drains or anything like that, you have to be very, very careful when you're dissolving them, because they can get really, really hot, and then it can get quite dangerous. Calcium chloride, which is a type of salt, it's what's used in some disposable heat packs. So inside the heat pack, there's a little vial of water, and you crack that, and the solid then dissolves in the water. And as it dissolves, it heats up. Those can get to about 40 degrees just by dissolving some solid in a little bit of water. But on the other hand, there's stuff that actually gets colder when it dissolves. So ammonium nitrate, for example, is a kind of classic example of that. And that's what's in disposable cool packs. Again, you crack a little thing inside that has some water in it, and as the ammonium nitrate dissolves, it gets cold. You can use that as an ice pack when you've got an injury, for example.
Question of the Week is part of the Naked Scientists podcast and supported by the Wellcome Trust and UK Fast. Look us up online at nakedscientists.com.